Namaskara. In this session, we continue our discussions on greedy algorithm, and we are going to look at another algorithm for minimum spanning tree, and this algorithm is designed by Prim. So, this is Prim's algorithm for minimum spanning tree. Okay. So, we take this opportunity to introduce certain basic properties that are going to be helpful in arriving at the design of this algorithm. We say that let G equal to V E W be a connected, undirected, weighted graph. The weight functions are defined on edges. Weight of an edge is defined by WE, and if E equal to XY, then we denote that by WXY. It depends on the notation, WXY or WE. Okay. Now, a cut of G is a partition of a vertex set, is a partition of vertex set V into two parts. Okay. So, let us say S and V minus S. A subset of vertices and its complement. So, you can view, here you have S, here you have V minus S. Now, how can the edges of the graph look like? Probably both ends are here and both ends are here, or one end is here and one end is in V minus S. An edge may have both its end vertices in S or both its end vertices in V minus S. Such edges are called the internal edges. Okay. An edge XY is called an internal edge if both X and Y belong to S, or both X and Y belong to V minus S. So, these are called internal edges. If X belongs to S and Y belongs to V minus S, this edge XY is called the crossing edge. So, if X is like this and Y is like this, it is called the crossing edge. It goes across the cut. Okay. Now, an edge, we have already seen, we are going to build the edge set of the minimum spanning tree. Okay. Spanning tree is T, same vertex set, edge set A is a subset of the edge set E. then it is called a spanning tree. Weight of a spanning tree is, or cost of a spanning tree is sigma weight of the edges E belonging to E. Add all the weights of the edges, and here is one very interesting way to build a spanning tree. Okay. Suppose you are building T edge by edge, and you have already built up to some stage. Okay. Let A be a subset of edges of some minimum spanning tree. Currently, let us assume that you have got some subset of edges of some minimum spanning tree. You do not have the full minimum spanning tree. You have only A. A may be only 3 edges or even 1 edge. It does not matter. Suppose it is a subset of edges of some minimum spanning tree. Let C be a cut of G for which all edges of A are internal. All edges of A are internal edges. That is, edges of A are either in S or in V minus S. That means no edge of A is a crossing edge in C. In this cut, no edge of A is a crossing edge. All edges of A are internal. Okay. Let E be a crossing edge with minimum weight let E be a crossing edge with a minimum weight, then A union E will be a subset of some minimum spanning tree. It could be the same or some other one, that depends. But this will also be a subset of some minimum spanning tree. Okay? It is a beautiful result. It is a well known, it is a nice mathematical result. We will see the proof of this later. There is an elegant cut and paste argument given for this, but for the time being let us assume that this is true. Okay? Proof we will see later. Okay, then A. So this shows that how to add one more edge to the current set of edges which you have in your hand and which is known to be a subset of some minimum spanning tree. You do not know the full minimum spanning tree, you know only some edges of some minimum spanning tree. How do I add one more edge to it? Find a cut for which all these edges of A are internal. Then in that cut there will be several crossing edges. There will be at least one crossing edge, that is because the graph is connected. If there is no crossing edge, then these two parts are disconnected component. That is not the case. The graph is connected. So surely there will be some crossing edge. Among all the crossing edges, find the minimum weight crossing edge, find the minimum weight crossing edge and add that to A, it is guaranteed to be a subset of a minimum spanning tree. Okay. So, this gives us the following plan, the algorithmic plan. Okay. To begin with, A equal to empty. Empty set is a subset of any set. Let A equal to set. Now, n minus 1 times you have to add edges to A, because minimum spanning tree, for that matter any spanning tree, will have n minus 1 edges where n is the number of vertices. If cardinality of E equal to n, cardinality of E equal to m, any spanning tree will have n minus 1 edges. So, I am going to keep on adding edges n minus 1 times. So, for I equals 1 to n minus 1 times, what is that I am going to do? 1. Find a cut that has edges of A as internal edges. Any cut will work. Okay? Any cut for which the edges of A are internal will work. Edges of A. Find a cut that has edges of A as internal edges. Let E be a minimum weight crossing edge. Find this E. Okay? Let E be the, find E which is a minimum weight crossing it. A equal to A plus E. Update A. Now find a cut that has got edges of A as internal edges. Let E be a minimum weight crossing edge. Add that. So, in this way n minus 1 times when you add, you have n minus 1 edges added and you have a tree which is a subset of a spanning tree. A spanning tree can have only n minus 1 edges. That means this is the set of all edges of that particular spanning tree. Done. Therefore, this gives you a kind of a plan, a generic way to think of designing an algorithm. Okay? This is greedy algorithm because every time you make a minimum choice, minimum weight crossing edge. Notice that you have flexibility in designing a cut. All you need is a cut that has got edges of A as internal edges. There can be several cuts and you can choose any of them. This method will work. You can choose any cut. So, for the sake of implementation, we have to choose cleverly a cut that is easy to obtain. It is easy to construct. Computationally, quickly build that cut. After getting the cut, you have to anyway find out the minimum weight crossing edge. Okay? We will represent a cut by S and V minus S. S, V minus S denotes so every vertex either it is in S or not in S. If it is not in S, it is in V minus S because it is a partition. So, a crossing edge is easy to, whether an edge is a crossing edge or internal edge, easy to determine if we maintain a flag, okay, in S for every vertex V. We maintain in SV equal to 1 if and only if V belongs to S, and equal to 0 if V does not belong to S. Let us maintain a Boolean array and we update this whenever the status of a vertex changes, you change it, okay. So, in S V will be 0 if V is not in S, and now A is empty. Which cut I can choose, so that all edges of A are internal. Any cut you can choose, A is empty, there are no edges after all. So, the simplest of all cut is choosing a vertex and putting remaining in V minus S, okay. So, let R be a vertex in V, any vertex you choose. Define S equal to R and V minus S therefore is V minus R. Now, in S R equal to 1, because R is in S, and in S V equal to 0 if V is not equal to R. Right. All others are not in S, therefore, this is how the current partition is represented by this. This is how you initialize. You choose a vertex and then set this Boolean array like this. You would have started off with a partition. So, after finding a cut, how do you find a minimum weight crossing edge? How do you find minimum weight crossing edge? You have to list all the crossing edges and then you have to figure out among the crossing edges which one is having the minimum weight. How can we find this? A naive way of doing that is examine all edges. If it is a crossing edge, consider its weight. If it is not a crossing edge, ignore it, because we are interested only in the minimum weight crossing edges. But how do I know whether an edge is a crossing edge or not? It is very simple, right. If you take x, y, if in Sx equal to in Sy, both of them may be 0, both of them may be 1. In this case, the edge xy is internal. The edge xy is internal. If in Sx not equal to in SY, then the edge XY is a crossing edge. One of them is 1, it is undirected graph. One of them is 1, another is 0. Okay. If in S not equal to in SY, then XY is a crossing edge. Therefore, whether it is a crossing edge or not, I can determine in constant time. So, I simply consider all edges of the graph. Okay. If it is crossing edge, I consider its weight, right. Otherwise, I do not even consider it. So, and I update my minimum weight crossing edge if the weight of the new crossing edge is smaller than the weight of the current minimum. So, it is very simple. Scan all edges and determine the minimum weight crossing edge. So, one idea is scan all edges and determine a minimum weight crossing edge. Okay. Scan all edges and determine a minimum weight crossing edge. Therefore, the complexity for this is order E, which is order M, because for each edge you are checking and comparing, and this step is order M. Whatever is the cut, and A equal to A union minimum weight crossing edge. Let this minimum crossing edge be E, and A equal to A union E. This is okay. This is very simple to implement. Just add E to A. You can maintain A as a linked list. You can maintain A in several ways. Whatever is the way, you add this edge to that collection, represent it accordingly. A is A union E. Now, I have to come up with a cut that is having all the edges of A are internal. A is updated. But how is A updated? Look at the scenario. I have this, all edges of A are internal. There are several other edges. I have added this XY. I have added a new edge XY. A equals, this is the edge E. A is A union E. How to make this edge internal, for what cut this edge E would become internal? I move Y to S. This is S, this is. So, move Y to S. But this is very easy to implement. Y is in V minus S means in S Y will be 0. You make in S, this will move Y to S. Just make the 0 to 1, update the 0 to 1. Earlier it was not in S, now it is in S. When it is in S, X, Y is also here. There are other edges. You can see that all edges of updated A are now internal edges. Here is a new cut. With respect to this new cut, all edges of A has been, because there is only one crossing edge that you have added. Whenever you are adding a crossing edge, the vertex in V minus S, you move to S. That edge will become internal to S. You can see that xy, now y is also in S, x is already in S. So xy has become an internal edge. That is it. Now you have a cut. Now with respect to this new cut, find the minimum weight crossing edge, add that to E. Therefore, our refined plan is something like this. Okay. Let S equal to R, V minus S equal to V minus R. Let this be the cut. Okay. This cut, this is the cut. Find for I equal to, I have a cut and I have A and I have a cut with respect to which so find an edge, find a crossing edge step 1, find a crossing edge x y with minimum weight. Here x belongs to S, y belongs to V minus S. Find a crossing edge with minimum A equal to A union xy. Add this to A. So A is updated. Now we update the cut. Update the cut so that the new cut has all the edges of updated A as internal. So what is involved in updating of A? Updating of the, sorry, what is involved in updating of the cut? Updating of the cut simply involves moving y to, this simply is move y to S. That is it. Move y to S. When you do that, the cut is updated. Now again go back, find a crossing edge with the minimum weight, add that, update the cut, find the minimum weight crossing edge. Okay. So finding the crossing edge with the minimum weight takes order m. Our naive algorithm is consider all edges, ignore internal edges. If it is a crossing edge, consider its weight. So in this way consider all crossing edges and find a minimum weight crossing edge. This is order 1, and moving, we have seen order 1. It is simply setting a Boolean value from 0 to 1. Therefore this is order 1, this is order 1. So essentially the complexity is order m, and you are doing n minus 1 times. Therefore, this algorithm, the naive algorithm, or finding the minimum weight crossing edge by a naive way, is order nm. Naive algorithm is order nm, because you are not doing anything other than finding the minimum weight crossing edge by looking at all edges. All right. So, let us see how we can improve the complexity. Do we have to every time go through all edges and find the minimum weight crossing edges? We can reduce the cost if we have the following piece of information. Okay? So, here is one piece of information that we would like to have that will help us. Consider the, I am drawing only the crossing edges. These are all crossing edges. Okay. Let us assume that I have drawn our crossing. This yes. Suppose for each vertex V, in S, I maintain the partner of V in V minus S. This is called the partner of V. V belongs to S, partner of V belongs to V minus S. Partner of V belongs such that VPV has the minimum weight. It is a minimum weight edge from V. Now, let us assume that VPV is the minimum weight edge from V in S. From V there are several crossing edge. VPV is a minimum weight crossing edge from V. Suppose I maintain this information for every vertex in V. Okay. Suppose I maintain this information for every vertex in V. Suppose VPV is known or maintained for every vertex V in S. Then how to find the minimum weight crossing edge? It is very simple. Find the minimum weight crossing edge among VPVs, because from V I know the minimum going out. For every V I know the minimum that is going out. So the overall minimum is minimum among this. Then the minimum weight crossing edge can be found as minimum among VPV with V belonging to S. The minimum weight crossing edge is nothing but the minimum among these kind of edges, right. From each vertex I know the minimum weight crossing edge. So find the overall minimum, and that will be the minimum weight crossing edge from S to V minus S. And this can be computed, obviously this can be computed in time proportional to the size of S, in proportional to the size of S, because if S has got 10 vertices, from each vertex I have VPV, find the minimum among the 10. So it is going to take time proportional to size of the set S. S is a growing set because we move one element from V minus S in each iteration. Initially cardinality of S was 1 because S has got only one vertex, and then you keep adding in each iteration one vertex, so it becomes 2, then 3, then it becomes n. But anyway, cardinality of S is always less than or equal to n. Therefore, in maximum order n time we can find a minimum weight crossing edge, provided we maintain this information. We maintain this information. We have to maintain this information, then only we can find the minimum weight crossing edge. Okay. Therefore, now how do we maintain this information? When we add an edge, this changes, right. For example, this is a minimum weight crossing edge, let us say x, y. This may be the partner of x. Well, this may be even the partner of this vertex, and this could even be the partner of that does not matter. But you have to move x, more to move y. When you move y, x, y, this becomes internal. But what about, let us say this is y, this is x dash, this is x double dash. Who is the minimum weight partner now after moving y? And for x dash, who is the minimum weight partner? For x double dash, who is the minimum weight partner? Because their minimum weight partners is moved already. Therefore, you have to find the minimum weight partner for everybody in the updating process. We will see the implication of this and the cost of this in our session where we continue the discussion. Thank you.